We left off yesterday in the middle of the suffix array construction chapter, and I was about to show you this very elegant method that allows you to construct suffix arrays in linear time by a fairly simple method. At least every single step is fairly simple. And here's the method again, which is much nicer than the corresponding algorithms for suffix trees that I did not even dare to show you. So this is the suffix array construction algorithm I'm talking about. It consists of those three steps. We first recursively compute the rank array of suffixes that don't start at a multiple of 3. Then we use this to induce the ranks for the suffixes that do start at a multiple of 3. And finally, we merge those two together to get the rank array for the entire list of all suffixes. I'll fast forward through these. We've seen that in detail. So the first step could be done fast because we could use these ranks from the first step, the recursively computed R12s, to compare or sort any two suffixes that start at a multiple of 3. Replace that by the equivalent problem where we have just one character and then one rank from this rank array, one entry of this rank array. So that's how we could do step 2 in linear time. And step 3 was this merging of the two sorted lists, where we used that to compare two suffixes of different color by splitting off 1 or 2 of the first characters. We always end up in the blue range, in which we can use the indices in the rank to compare which of the two suffixes is smaller, and so solve the merging problem. So we could also do that in linear time. Now, to see if you remember all those definitions, I'd like you to do again this recap question. I'll leave 2 minutes. Hopefully that will be enough. So here's again. Sorry, that was the wrong question. That's the right question. Sorry for starting the wrong one. So just a recap of the definitions, because what we will cover today will again build on those. I'll switch back to this view. It's partly overlapping with the question from last time. That's on purpose. Okay, I don't know if you're already through. Maybe you can post again a quick OK, but I guess I'll leave a few more seconds. I don't know how much you lag behind me in this. You could actually see it if the live stream has a different time left than what you see in the Pingo window. You should be able to figure out what the lag of the stream is. So 10 more seconds to complete your vote. I wish there was an option for 1.5 minutes. It seems 2 minutes is a bit too long, and 1 minute might be a little short, but we've already made it through. Good. Okay, so let's see the results, and I'll highlight the correct answers. It was a trick question in the sense that almost all answers were correct. Indeed, the only answer that was wrong was the second one. So I'm happy that many people clicked most of the answers, but then for the last one you didn't seem to be very confident. So let's go through those quickly one by one. So yes, L is the suffix array which stands for leaves or left. Left was this picture where we had the suffixes in sorted order. So sorry, suffixes in text order on the left, and then the picture where the suffixes were sorted lexicographically. And we had these two arrows that go back and forth. I guess you remember by the picture what the slide looked like. That's where the left comes from and where the right comes from. So left, R goes from left to right. That's the suffix array. And the rank array, R stands also for rank. The inverse suffix array goes from right to left. Hold on, I'm confusing myself. It goes from left to right. It's the direction. Oh dear. Okay, good that we covered this again. L lists the leaves of T in left to right order, and that's the same as saying it lists the suffixes in lexicographic order. That's why you see L here. So that would be L, and here you would see R. So once again, L is going to the left and R is going to the right. I do get confused about this myself. I know it's a little tricky definitions. That's why I wanted to repeat them again. And the connection between the two is simply this. They're the inverse of each other. So if you would put L of R of I, you would always get I back. That's what is meant by the inverse. All right, so much for the repetition. I guess keep that picture in mind, going to the right, going to the left. That's how the arrays were defined. Now we left off with this problem in the suffix array construction. We managed to do these two critical steps in linear time, but then step one, there was in a sense a mismatch between the definition of the problem and the instance that we would like to recurse on, that we would like to apply the algorithm recursively on. The problem is that we need a single string t prime that we can recurse on and on which we compute the ranks of all its suffixes, whereas the question that we ask only includes the suffixes starting at not multiple of 3 positions, so that's a mismatch. But there's a neat, somehow ingenious, clever trick how you can fix this problem. And that's one of the main inventions of this algorithm, the DC3 algorithm. You combine several characters into a single one, in our case triples, so this ABC is a single character now. And then you can form suffixes at certain regular positions. So for example, if you take our favorite banana band and apply this construction, it only has 4 characters. And if you take the suffixes of this t box, so t box, whenever I have a string box means take the first 3 character and make it a boxed character, a triple. Take the next 3, make it the next, and so on. And we'll append enough dollars so that you always end up with a multiple of 3 numbers of characters. If you take the suffixes of this t box, then you get exactly the whole string, the suffix starting at position 3, at position 6, and so on. So you do get exactly these suffixes that start at multiples of 3. Now this is not exactly what we need. We want the ones that don't start at a multiple of 3. So start at 1 and 2, 4 and 5, and so on. But with a slight twist on this, we can get those. We take the suffix of t that starts at 1, and we take the box that gives us all the suffixes 1, 4, 7, and so on. And we take the suffix of t starting at this at position 2, the third character really, that gives us the positions 2, 5, 8, and so on. And if we take the concatenation of those two strings, put them both next to each other, we actually get both of those. We get the ones that start at, well, a multiple of 3 plus 1, and we get those that start at a multiple of 3 plus 2. And on this string, that's our t prime that we try to recursively construct the rank array for. Now, there's still a problem with this approach. And this is a little bit subtle if you think about it. The problem comes from the fact that in each recursive step, whenever we apply step 1, we take triples of our character, and that means the alphabet cubes in size. If we start with sigma characters initially, then after the first step, it's sigma cubed, and then it's sigma cubed cubed, so sigma to the 9. And that's really bad. That grows very, very quickly. Now you could say, I don't care, why is having a large alphabet a problem? If you go back to how we solved those steps 2 and 3, they relied on the fact that we have a linear time sorting method for individual characters. Remember, for example, step 2, that we had pairs of a single character and the rank. So if this alphabet just grows without any bounds, we cannot apply linear time sorting anymore, and the whole complexity of the algorithm won't be linear. Now it's true that the alphabet can be very big and it grows in each step, but we only have so many characters in the string that we construct. This t prime has, well, roughly 2/3 n triples. We cut the length of t in thirds for the first instance. So what I mean is there's 1/3 n over 3 comes from this, n over 3 comes from this, and then 1 or 2 more we don't care so much. So we don't have too many characters that actually occur. So even though the alphabet is really big, many or most of those characters cannot be used in our actual string. So we can compress the alphabet to only contain those character triples that actually occur in our string t prime. And that's what we do. So to do that, we sort all the occurring triples. Again, that means sorting essentially means 3 rounds of counting sort. So it's by the same tricks we used in step 2. We can do this in linear time. And then we replace those triples by their rank in sigma. I'll show you an example in a second. So the key point is that if we do this in each round, we keep the alphabet size less than n, and actually it shrinks because the length of the string is going down also. This is also a reasonable assumption initially. It's always fine to limit the alphabet to the number of characters in the string, because any other character can't really be used. We cannot use more than n characters. A couple of people have been posting that they didn't manage to sign up for Pingo. I'll open it at the end again. Don't worry. All right, so we have to reduce the alphabet to get this going. Here's a simple example for that. Our string from the examples before. That's the whole text. That's the suffix that omits the first 2 characters. And here, so remember, this is the construction. We take the suffix that starts at 1. So we delete the h. And then we apply this boxing construction, meaning we build triples of characters up until the end. And here, well, I have to pad my string with dollars. So whenever you run out of characters, you just add more dollars if you need. Then to be on the safe side, we add another triple dollar in between to keep those two separate. And then we do the same thing. We do the boxing construction on T2, and that gives us that. In that case, it turned out we already end, so we don't have to do a double, triple dollar. Well, what a word. But it also doesn't hurt to add it. Now, almost all of those triples in this example turn out to be unique. It's just Anna that occurs twice, so these are the same. But other than that, these are the triples that occur at least once, and well, the dollars also, that's the second one. Now, this is our effective alphabet. The true alphabet here was all triples, but those are the only ones that ever occur, so we might as well take just those. Now we sort those and assign them ranks from, well, 0 to 12. There's only 13 here. And then we take our string t prime, as we had it here, that's the same, and we just replace every triple by its rank. Once we've done that, we can then set our size of the alphabet to be 13, the number of actually occurring triples, and that way we can continue with the recursive call. So that finishes the discussion of the suffix array construction. This is, once you've done this reduction, no more cheating, no more tricks hidden somewhere. This is all you have to do. So it's in 3 different ways, if you like. We apply counting sort. It's always the same trick. Back in Unit 3, I mentioned this, that if we are sorting integers, and well, characters are nothing but integers. If you're sorting integers and the range is not too big, you can do it in linear time. And here we applied this idea over and over again until, with the help of this clever recursion of 2/3, 1/3, we could reduce the whole problem of sorting suffixes to sorting integers from a small range. That's the ingenuity of the DC3 algorithm. Now for suffix arrays, a little intermediate summary. We indeed found a data structure that uses much less space than the suffix tree. Remember, it's only about the constants in the theta of n. So both are theta of n space. But whereas the suffix array had a very big constant, at least 10 words per character, we can get this down to a single word, a single number for the suffix array. And that's still enough to support the main application of this chapter, the text indexing. So we can reduce the space by an order of magnitude or more without sacrificing a lot in speed. We've also seen this simple construction, a very simple one that's easy to implement. I'm talking about the fat pivot string quicksort. And I've shown you, we just finished this, the linear time construction, which is a theoretical breakthrough and is also fast in practice. There's other methods that are used for this. In summary, you can say suffix arrays are really a practical data structure that you can compute fast, you can construct them efficiently, and there's simple methods that get the job done fairly quickly, and there's sophisticated methods that get the job done even more quickly if you invest a little more time in implementing them. There are some downsides. The theoretical time for string matching grows by this factor log n. So if your text is really, really, really big, this might be a headache for you. And the other more fundamental problem is that we didn't use suffix trees only for the text indexing, for the plain string matching, but indeed we applied it to other interesting problems. I sold you I sold you suffix trees as a magic data structure for solving all kinds of string problems, and now it seems we're back to just the string matching with the suffix arrays without a big chance to get all the other problems solved.